Financial Modeling, Topic 10, Portfolio Risk and Return, and Optimal Portfolios. Copyright Lou Gaddis. In this topic, we'll compute the historical mean and standard deviation of stocks, bonds, and bills using a 90-year sample, estimate future returns using historical risk premiums, compute portfolio risk and return using correlations and covariance matrices, and compute optimal portfolios and efficient frontier. We'll start with data from DeModern that has the returns of the S&P 500, 10-year Treasury bonds, and Treasury bills from 1928 to 2015 or 16. So I have this data, and you can see that the return of the S&P 500 in year 1928 was 43%. You can see the stock market crash, the recession, a bit of a rebound, and some more bad years. And what you notice is it's very volatile. On the other hand, here's the returns of bonds. Looks like they're between, say, -2 and 8%, so not as variable as stocks. Now, these are not just the yields on, or these are not the yields on bonds. The way you have a negative return on a bond, since bonds prices are sensitive to interest rates, I presume that interest rates went up this year, and if you owned a bond, you actually took a loss. And what you see is it looks like there's no negative values on T-bills. So these are 3-month Treasury bills. So they're very insensitive to interest rate risk. So you can see that you get, looks like a 0 to 3 or 4% return per year. So that's our data set. And the first thing we're going to do is calculate historical returns. So I'm going to give these named ranges. Let's call this one here, this whole range from the first value to the end. I'm going to call that stocks. So that's a named range. I'm going to call this one bonds. And I'll call this one bills. So let me take the average of each column. I can say, give me the average of stocks, the average of bonds, and the average of bills. So you can see over this 90 or this almost 90-year history, stocks return 11.4%, arithmetic average, bonds 523, and bills 349. And historically, the return of stocks has been (6.18% above bonds. And that's important because now we're living in a much lower interest rate environment. The current T-bill rate is about 14 basis points and 160 basis points for bonds. So if we were looking what our portfolio would do today, it would look more like this: 14 basis points and 1.6% of the current yields on bonds. So that would be the expected return, assuming interest rates don't change. Now, the reason I'm not going to use 11% is we're just living in a lower interest rate environment. So if I, on average, earn 60% above bonds, I'll take my current bond rate plus that spread, that risk premium, and that would be, say, my guess for stocks going forward, 778. So we're going to, in a minute, or a few minutes, build a portfolio of these stocks, bonds, and bills using these returns. And what we're going to do is we're going to create optimal portfolios that maximize return for some level of risk, or minimize risk for some level of return. And the measure of risk we're going to use is going to be standard deviation. So let's calculate the standard deviation of stocks, bonds, and bills. And what you can see is stocks are the most variable, 19.82%, followed by bonds and bills. And you can see that a different way. I did a histogram of the 90 years of stocks, and you can see that the mean was about 11%, And you can see the dispersion around that mean is very great. On the other hand, bills had a mean of about 3 or 4%, and the dispersion was very narrow. And if I fit this bell-shaped curve over this data, it really doesn't look too good for stocks. Looks okay for bonds. Not sure about bills either, but our primary measure of risk in finance, we're going to assume that these asset returns are normally distributed as a computational shortcut. That way, all we need to know is the mean and the standard deviation of a portfolio or an asset, and that'll fully describe the distribution. All right, so the primary measure of risk, if you assume a normal distribution, is standard deviation. Standard deviation is the square root of variance, and it's a measure of dispersion around the mean. Again, dispersion around this mean. Standard deviation, again, is the square root of variance. Variance is the average squared deviation from the mean. So if I took each one of these values, say for stocks, and took the distance or the value between, say, this return here and the average and squared it, and took the average of all the squared deviations from the mean, that would be the variance. Take the square root of that, and that's the standard deviation. All right, the history of the standard deviation comes from some early statisticians interested in trying to estimate probability of random events. So for example, if you flip a coin and get a head or a tail and take a distribution of a number of flips, say take 12 flips, you can get a certain distribution. Once in a while you get one head and 11 tails, and once in a while you get one tail and 11 heads, and usually you'll get about 6 and 6. So even though the flip is random, when you aggregate the data, it looks very well behaved. If you use the normal curve, or if you assume the normal curve, you can fully describe the distribution. So for example, if I take these two areas, 68.2% or plus or minus 1 standard deviation. If I add in these two areas, about 95% of values are plus or minus 2 standard deviations from the mean, and about 99.9% of the time you'll get plus or minus 3 standard deviations from the mean. So we're going to use our primary measure of risk as standard deviation, and stocks are the riskiest, bonds are next riskiest, and then bills are the safest. And this is just looking at if our stock returns were normally distributed with 8% mean and a 20% standard deviation, just rounding. We can then say that 68.27% of the time we're going to be plus or minus 1 standard deviation. So I'll take 8 plus 1 standard deviation, that's 28%, and 8 minus 1 standard deviation, that's minus 12%. So 68% of the time, my stock return, if this is the stock return, is going to be between negative 12 and positive 28%. And I would be 99% confident it's plus or minus 3 standard deviations. So that would be 8 plus 60% or 8 minus 60%. So if we assume that stocks are normally distributed with a mean of 8 and a standard deviation of 20, 99.73% of the time, I'm going to have a return between negative 50% and positive 68%. And this also leads to a statistic called VAR, or value at risk. VAR tells us the worst case scenario for a portfolio. What is the worst case loss for a portfolio? Well, it's not really the worst case. It's the worst case in a probabilistic sense. So for example, if someone told you that 95% 1-year VAR and gave you a value for that, what that means is that you're 95% confident that losses will not exceed that value. Now the formula for that is the mean minus 1.65 standard deviations times the portfolio value. So the 1.65 is the Z statistic that corresponds to a 95% confidence interval one-tailed test. So looking at a normal distribution, we'd only expect 5% of the time to have a value or an outcome that is more than 1.65 standard deviations lower than the mean. So what we're talking about, we're 95% confident that we'll have our losses will not be larger than 1.65 standard deviations from the mean. So if I did this calculation for a $100 portfolio invested on a portfolio that's normally distributed with a mean of 20 and a mean of 8 and a standard deviation of 20, I would get $25. We'd call that the 1-year since this is 1 year standard deviations and means, we call it the 1 year 95% confidence interval VAR of $25. And what that means is you're 95% confident losses will not exceed $25. However, there's a 5% chance that losses will be $25 or more. So let's talk about portfolio means and standard deviations. I want to create a portfolio that's 60% invested in stocks, 30% in bonds, and 10% in bills. Now, the expected return of that portfolio is pretty simple. It's really just the weighted average return of each asset. So the way we write that is the return of the portfolio of n number of assets, so say 3 assets, is the sum from I equal 1 to 3, WI-RI, where W is the weight in each asset and R is the expected return in each asset. So how I'd use this formula is you can think of this sum as a counter. It counts from 1 to 2 to 3 if you have 3 assets. So it counts from 1 to 2 to 3. So I'd set I equal to 1 and then plug my formula in, W1R1. So it's the weight of the first asset times return of the first asset. Set my weight, or my I to 2 and plug in WIRI, the weight of the second, and so on. And then since this is a summation, we're just going to sum up these 3 values. Now in Excel, the easiest way to do that is just use my sum product. So I'm going to come down here and I have some weights plugged in here, 60, 30, 10. So if I want the mean of a portfolio, I can just say it's the sum product of my weights and my returns. So I expect that portfolio to give a 5.16% return. Now I'm going to try to calculate the variance of the portfolio. Now the variance of the portfolio is a lot more difficult. It's not the weighted average. It's not the weighted average because these assets we're going to assume are not perfectly correlated. And if they're not perfectly correlated, your variance or standard deviation are both going to be less than the weighted average because of diversification. Now the formula for calculating this is this nasty thing right here. The variance of an n asset portfolio, say 3 assets, is written sigma squared p. Sigma squared is the variance. It's the double sum from I equal 1 to n, j equal 1 to n. These are just 2 counters, wi, wj, sigma ij. Now w are the weights in the assets. Now sigma ij is a notation for a covariance term. A covariance is a product of 2 standard deviations and a correlation. So the covariance between, say, stocks and bills is the standard deviation of stocks times the standard deviation of bills times the correlation between stocks and bills. Now, which makes sense if you think about what this is trying to measure. It's trying to measure how these covary. So that's a function of how risky each one of them is, how variable each one of them is. That's the standard deviations, and how they tend to move together, which is the correlation coefficient. Now, how I'd implement this formula in a table is I'd set I equal to 1 and set j equal to 1, 2, 3. Set I equal to 2 and j equal to 1, 2, 3. Set I equal to 3 and j equal to 1, 2, 3. And then I would just plug in my wi, wj, sigma ij. So when I is equal to 1 and j is equal to 1, it's the weight in the first asset times the weight in the first asset. That's the weight in the first asset squared, plus the covariance between the first asset and the first asset, which by definition is the variance of the first asset. And then I said I equal to j equal to 2, and I get weight of 1, weight of 2 times covariance between 1 and 2, and go and forward. So what this does for us, this double summation, it makes sure we account for all the different pairs of assets. So there's 9 pairwise combinations of 3 assets. And to fully calculate the variance, I need to know how each asset covaries with the other. So we're going to build this in Excel, except this is kind of a hard way of doing it. And what we're going to do is these 9 numbers, these 9 pairwise combinations, we're going to write them this way. So here's 1 with 1, 1 with 2, 1 with 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. So if we can write it this way, it looks like all we need to know is the weights in every asset. We know that, right? 60, 30, 10 are the 3 weights. And we just need 9 covariance terms. Now, normally in finance, we don't start with the covariance terms, although we could. We normally start with a correlation matrix and build the covariance matrix. So let's do that. So the correlation matrix, the correlation between all the different assets. Let's first put in ones. Every asset is perfectly correlated to itself. Now we just need to know the correlations between the different assets. We can say equals correl and do stocks and bonds. So the correlation between stocks and bonds is negative 0.03. That means it's almost zero. It means these are almost random independent events. I'm going to copy that there and just do stocks with bills. Looks like that's also negative 0.03. And then we can do bonds with bills, which is a 0.3. So bonds and bill returns tend to move together. Now these are the only unique variables, these three. Stocks with bonds, stocks with bills, and bills with bonds. These on this the top half, top right of this matrix are just repeating numbers, right? This one here is bonds with stocks. This one here is bonds with stocks. So I can just say equals that. And bills with stocks is the same as this. And bills with bonds is the same as this. So this is my correlation matrix. From this, I can calculate a covariance matrix. Remember, a covariance is the product of two standard deviations times a correlation coefficient. So I'm going to do a little trick here. I already set up, I'll do this, start this from over. I'm going to set up a little transpose. I'm going to highlight this 3x1 matrix or array and say equals transpose. And I'm going to highlight the standard deviations and hit Control-Shift-Enter to enter as an array. Now these are my three standard deviations. Now why I'm doing this is just going to make this a little bit easier because there's no easy way to anchor this. Each one of these values is a correlation from above times two standard deviations depending on where it is in this matrix. However, if I do it this way, the correlation between stocks and stocks times the standard deviation of stocks. Now that's in row 99. I'm going to anchor 99 times the standard deviation of stocks, and I'm going to anchor F. Now that is perfectly set up that I can just copy down and copy over. So if you notice, the covariance between bills and bills is the correlation between bills and bills times the standard deviation of bills times the standard deviation of bills. And now we're ready to do our last step. The variance of an asset portfolio is this. It's all the covariance terms times the weights. So what we're going to do is do the same thing. I'm going to set up a weights transpose. My weights are 60, 30, 10. I'm going to make a transpose. Got to make sure these are not values. They got to be linked. So these are linked. So if one updates, it updates the other. So all I need to do is take a covariance times a weight in row 110. Keep that in 110. Times a weight in F. And there's my variance calculation terms. The sum of these 9 numbers is the portfolio variance. And if I take that to the square root, 1/2 power, that is the portfolio standard deviation. So that's how you calculate the standard deviation of portfolio. Now notice all these will update. If I make this 100% stocks, this is the mean and standard deviation of stocks. If I make it 100% bills, notice I have a summation here to make sure I've invested all 100% of my money. That is the mean and standard deviation of bills. Let's change it back to 60, 30, 10. All right, so that's how we calculate the mean and standard deviation of a portfolio of assets. The last thing I want to do is let's build an efficient or optimal portfolio. An efficient portfolio is one that maximizes return for a given level of risk or volatility. Usually we call standard deviation volatility, or minimizes volatility for a given return. A set of efficient portfolios is called a portfolio envelope or efficient frontier. So what we're going to do is we're going to calculate 9 possible efficient frontiers. And those are portfolios that have these means. This is my lowest asset mean. So if I'm 100% bills, the lowest return I will get is 14 basis points. If I'm 100% stocks, the highest return I can get is 778. What I'm going to do is I'm going to run solver and find a portfolio that changes these weights such that it gives me a mean of 14%. We'll make sure 100% of our money is invested, and it minimizes the volatility. So I'm going to do that. Data, solver. I'm going to reset this. Well, looks like I'm not going to be able to do that easily. Oh, there's reset all. So I want to minimize my standard deviation right there by changing these 3 weights. I'm going to add a constraint that 100% of my money is invested. Make sure that's a formula. So that equals 1. And add a constraint that this value here, this is our first portfolio, is equal to 0.14%. I'll make sure this box is checked because we want to make sure the weights are all positive. We're not selling these assets. And we'll solve. And what you see is the portfolio is has a 307. I'll copy that as a value. And it's invested 100% in bills. And I can do the next portfolio. Let's find the best 1% portfolio. I'll go to solver. I'll change this constraint to 1%. I'll rerun it. And my best 1% portfolio looks like 9% in stocks, 13% in bonds, and 78% in bills. And gives me a portfolio volatility of 330. And if I continue doing that, I would get these 9 portfolios. And if I graph these 9 portfolios, we call this our efficient set or efficient frontier or envelope. So there are other portfolios, like here's a portfolio here that's 100% bonds. All right, so I just added bonds to this graph. By the way, to get this graph, you just highlight these 2 columns here and insert an XY graph or XY scatter graph with line. Now these are the only portfolios I want to invest in. So let's look at this bond. So this is 100% stocks, this is 100% bills, but this one here is 100% bonds. Notice it's fully dominated. I would never hold this portfolio in isolation because I'd rather be closer to, say, one of these portfolios that have the same level of return but less risk. Or I'd like to be maybe between portfolio, was that 3 and 4. These portfolios here have about the same level of risk but higher return. So now it's just a matter of which portfolio you choose. Usually has to do with your age. When you're younger, you'll take more risk because there's more chances for, on average, the portfolios to even out. When you're older, you don't have as much of a runway, and you just want to make sure you have a safer portfolio. But these would be the only portfolios you would choose. And again, no one would hold bonds. So in this topic, we talked about how to calculate the historical means and standard deviations of stocks, bonds, and bills. We estimated future returns using historical risk premiums. We computed portfolio risk and return using correlation and covariance matrices, and we computed optimal portfolios